Great to have you back here. And the title of this talk is Black Holes and Boyle's Law, the thermodynamics of Einstein's greatest blunder. So let's welcome Brian.
Thank you. Okay, the talk today, I'm afraid, is going to be very conceptual. I'm not going to be talking about any real physics, and I apologise for that. I'm sure, as I'm sure most of you know, Einstein's greatest blunder is the introduction of the cosmological constant into his field equations. And Cliff told us about dark energy yesterday and discussed the evidence for the cosmological constant. I'm not going to be talking about any of the observational consequences of the cosmological constant. I'm going to be looking at some of the conceptual issues that surround the thermodynamics of black holes. And this all comes from taking classical general relativity and looking at quantum field theory in the background of a curved space-time. And it raises some very interesting conceptual issues about the nature of black holes and an underlying theory of quantum gravity might be, though I won't be discussing quantum gravity today. So I apologise to any real physicists or cosmologists in the audience. What I'm going to talk about today is very much conceptual rather than anything to do with observation. And I hope I'll be able to convince you that some of the ideas are very interesting. I was told there'd be perhaps some PhD students in the audience or people who are not familiar with black hole thermodynamics. So I'll start off with a very elementary introduction to black hole thermodynamics and describe some of the ideas and concepts that lie behind it. And in the second half of the talk, I hope perhaps I'll be able to say something that might be of some interest to people who know a little more about it. So let's start with the notion of temperature and entropy for a black hole. The story goes back, I guess, 40 years now. If we take a Schwarzschild black hole, we know that there's an event horizon, and light cannot escape from the event horizon. And for an ordinary Schwarzschild black hole, that's twice the mass of the black hole, using Newton's constant to get the units right. So the event horizon is a sort of one-way membrane that things can fall into it, but nothing can come out of it. The area of the event horizon, of course, just using Euclidean geometry, 4 pi r squared. And an important parameter in understanding the black hole thermodynamics is the surface gravity. This is just acceleration due to gravity at the surface of the black hole. For a Schwarzschild black hole, the surface gravity works out to be 1 over 4 gm. I'm using units in which the speed of light is set to 1. This actually, this is the formula you get. It's the undergraduate formula you use for the acceleration due to gravity at the surface of the Earth. If you take acceleration due to gravity to be gm over r squared, that's the Newtonian result, and put in the Schwarzschild radius for r, you get the right answer. This is one of these situations where naive Newtonian reasoning actually gives you the correct relativistic answer. This is actually you can get this using the Newtonian formula, but the Newtonian formula doesn't work in more general situations. But for the Schwarzschild black hole, the Newtonian formula for the acceleration due to gravity at the surface of the event horizon gives you the correct general relativistic answer. The surface gravity will be important in what I'm going to say. So I'm introducing it at this point. Now, one thinks of black hole as being this voracious object that just sucks up everything. Mass falls into it and it just keeps growing, getting bigger and bigger and bigger. And to some extent that's true. But in the 60s and 70s, people began to realize that it's not the mass of the black hole that keeps increasing. That it is actually possible to reduce the mass of a black hole. If you have a black hole that's rotating, then you can throw things down into it and they can come flying out again with more energy than they went in, and you can use up the angular momentum of the black hole. And the mass of the black hole will actually go down. There are processes, classical processes, that can reduce the mass of a black hole. But it was noticed that in all of the formula that people were using, the entropy, or excuse me, the area of the black hole never went down. In any classical process that anyone considered, the black hole does keep growing in the sense that the area keeps growing. The mass doesn't have to increase, but the area always increases in any classical process. And given that the event horizon is a one-way membrane, that anything that falls in can never come out again, in particular, if information goes through the event horizon, it can never come out again. If you take your computer hard disk with all your images on it and throw the computer hard disk into the black hole, then you've lost all that information. You'll never get it back again. So in 1972, Bekenstein proposed that there should be an entropy associated with the black hole, and that the entropy should be proportional to the area. He suggested that perhaps the correct units to use would be the Planck length. So you divide the area of a black hole's event horizon by the Planck length squared. So essentially you're measuring the area in units of Planck areas. So Planck length, of course, 10 to the minus 35 meters. The length associated with the where we think that quantum gravity effects would become important, not relevant for any astrophysical black hole, an energy that corresponds to an energy of 10 to the 19 GeV, which is so large that we can never approach it in any laboratory experiment. But it's an energy scale that's relevant, believed to be relevant to quantum gravity. So you can use the Planck length to create this dimensionless. It's a dimensionless measure of the size of the black hole's area. And Bekenstein suggested that this should be associated with an entropy. But if a black hole has entropy, then it must have a temperature, one would have thought. And Hawking, in 1974, calculated the temperature associated with a black hole. It's a quantum phenomenon, so that's, I'm keeping units here, although I'm going to set the speed of light equal to 1. I'll keep Planck's constant in all of the formula to try and make it clear when something is quantum and when it's not. This is a quantum phenomenon. The temperature is due to quantum mechanics. It's not due to quantum gravity, though. It's quantum matter in a classical gravitational field. The Hawking temperature is associated with taking quantum field theory, electrons, positrons, quarks or gluons, and looking at the behavior of quantum fields for particles in a classical general relativistic particle. It is not quantum gravity. It's just like taking Maxwell's equations and treating electromagnetic fields as classical, but taking the currents to be quantum sources. So there's a temperature associated with the black hole, and it's proportional to the surface gravity. So if we put in the surface gravity for a Schwarzschild black hole, we get this formula here. The Hawking temperature associated with a Schwarzschild black hole is inversely proportional to the mass. Now this is a pretty amazing concept, because one wouldn't do, if a black hole has temperature, then if you put it in an empty space, then it's going to start radiating. And how can something come out of the event horizon? It was a very revolutionary concept when Hawking first proposed it. If we put in the values of put in the mass of the sun, a solar mass black hole, the temperature comes out as a few times 10 to minus 8 Kelvin. So it's of no relevance to physics, or no relevance to any kind of observational physics. These temperatures, of course, are achievable in the lab, but any black hole that's been proposed in an astrophysical context with the mass of the sun or greater will have a temperature equal to or less than this, and the microwave background is 2.7 Kelvin. So these things would not be relevant at all in any astrophysical concept, but in any astrophysical context. But the conceptual issues that arise from having this temperature are really fascinating and profound, and that's what I want to explore in this talk. Let me just, because I believe that there are people here who are not familiar with this, I'll briefly outline the idea of where this temperature comes from. In quantum mechanics, well, we have to. It turns out that the notion of a particle of general relativity is rather ambiguous. In quantum mechanics, first quantization, we take the Schrodinger equation, the finite independent Schrodinger equation, and if we want to quantize, for example, a harmonic oscillator, we write down creation and annihilation operators. You want to construct a vacuum, so the vacuum of your Hamiltonian would be the lowest energy state, annihilated by the annihilation operators. And we can construct a number operator, which counts the number of quanta in any quantum state in the Hilbert space. And for example, for free particles, or well, for a harmonic oscillator, I should have said rather than free particles, for free fields, the Hamiltonian is just the Hamiltonian is just the number operator times the energy of each particle. So a quantum state with n particles is it's n times the energy of a single particle. In general relativity, however, it's a little unclear what we might be doing here, because in general relativity, different observers have different times. The notion of time depends on the observer. And it can happen. So you'd have two different Hamiltonians, one associated with each observer, and it can happen that the Hamiltonians don't commute. And this, in fact, happens in space-time surrounding a black hole. And if the Hamiltonians don't commute, then the vacua could be different. And when we have this situation, what one can do is take the creation and annihilation operators in one basis, the prime basis, and you can always write the creation and annihilation operators in the unprime basis as a linear combination of the creation and annihilation operators in the prime basis. And this is something that's very familiar in condensed matter, and where instead of the creation and annihilation operators are for particles and holes, this is just these are Bogle-Uliff coefficients in a condensed matter context. And then we can ask, what's the number operator for the unprimed observer in the vacuum of the primed observer? And it's just going to be a sum over the square of these beta coefficients. Omega is the frequency, of course. And what Hawking did was Hawking calculated this. He took one observer to be an inertial observer at infinity, and another observer is an inertial observer who's at the event horizon. And he took so O prime is the vacuum as seen by an observer at the event horizon, and Hawking calculated and he showed that the observer at infinity would see the vacuum at the event horizon as being populated by particles. And he calculated these coefficients, and he found something that looked like a thermal distribution. It looks like a thermal distribution here for bosons, and he calculated the temperature in terms of the parameters of the black hole, and found that, well, I've written it in here as the Schwarzschild radius, but of course one can translate that into the mass. RH is twice the mass. So this is the Hawking temperature. It comes from calculating these Bogle-Uliff coefficients. So it's associated with the fact that you have two different times, two different Hamiltonians in the system. It's often described in a cartoon picture. It's often described as being, if you imagine near the event horizon, quantum fluctuations are continually producing particles and antiparticles. And the particles have positive energy and the antiparticles have negative energy. If the antiparticle falls into the event horizon, then the particle can then escape to infinity. So a positive energy particle is escaping to infinity, a negative energy particle has fallen into the event horizon, the mass of the black hole goes down, and the energy escapes off to infinity, and it goes off to infinity as thermal energy. It looks like heat coming out of the black hole. That's a very hand-waving description, and it introduces an extra ingredient into the calculation, which is actually necessary, because you can equally ask why can't the positive energy particle fall in and the negative energy particle out to infinity? You have to introduce a time asymmetry into the problem. At some stage, you have to postulate a time asymmetry in order to get the Hawking temperature. A black hole, in particular a Schwarzschild black hole, is a completely time-independent solution of Einstein's equations. And it's also invariant under time reversal. There's nothing for a black hole saying what's the forward direction and what's the backward direction. As a solution of Einstein's equation, it has time reversal invariance. Whereas if you introduce a temperature and say that there's thermal particles coming out of this thing, then you have a situation which is not time reversible. So at some point in Hawking's argument, he has to introduce time reversibility. Okay, so that's the basic picture. So once Hawking discovered calculated the temperature, then this opened the door to a full thermodynamic description of black holes. So In this slide, I'm going to describe the 4 laws of black hole thermodynamics. Zeta's law, in ordinary thermodynamics, the Zeta's law just says, essentially it says that if you have a system in thermal equilibrium and some mass of material and you break it up into 2 pieces, then each of the 2 pieces has the same temperature. But basically the temperature is uniform. In thermal equilibrium, the temperature is uniform everywhere in any system. For black holes, the temperature is associated with surface gravity, and it's known from all solutions of Einstein's equations that the surface gravity is always constant on the event horizon. So every point on the event horizon always has the same surface gravity. The acceleration due to gravity is the same everywhere on the event horizon. But that's not true of the surface of the Earth, of course. The Earth isn't quite spherical. The Earth is kind of, it bulges at the equator. The surface gravity at the North and South Pole will be slightly greater than the surface gravity at the equator. Because at the North and South Pole, you're slightly closer to the centre of the Earth than you are at the equator. For a black hole, the surface gravity is always the same everywhere, at every point on the event horizon. And if the surface gravity is associated with temperature, then the temperature is the same everywhere on the event horizon. So this is called Zeta's law of black hole thermodynamics. For the second law, we need to introduce entropy. A thermodynamic system will have an internal energy, which is a function of entropy. And in ordinary thermodynamics, the temperature is just the derivative of the internal energy with respect to entropy. In general relativity, we associate energy with mass. So let's take the internal energy to be the mass of the black hole. Then the first law of thermodynamics, we say that du is TdS or dm is TdS. So if that is the only thing that we're varying here, then we say that dm would be the temperature times the change in entropy. More generally, a black hole, we know that there's in 4 dimensions at least, a black hole is completely parameterized by its mass, its angular momentum, and its electric charge. There's nothing else that can change. If you know the mass, the angular momentum, and electric charge, you know everything about the black hole. There are no other macroscopic parameters describing a classical solution of Einstein's equations. So in general, the first law, the mass is associated with, well, we have the mass here. This is the Hawking temperature. The entropy is associated with the area. But we could also have an angular momentum J and an associated angular velocity omega. And we could have an electric charge Q and associated electrostatic potential phi. And this would be the general form of the first law for black holes. According to Bekenstein, the entropy is proportional to the area. And for a Schwarzschild black hole, that's the area is 16 pi n squared. I think I'm now using units. Yeah, I'm now using units where Newton's constant is set equal to 1. Hawking calculated the temperature. He said it's h bar over 8 pi n. The entropy is proportional to the area. We know the temperature, so we can put the temperature and the entropy in here. There's an unknown coefficient here, but it's just a constant. We can put the temperature and the entropy in here, and immediately we can deduce from well, the first law in this form, there's no angular momentum and no charge. From this, the first law in this form, the dm is TdS, you can work out the coefficient here. And you get this famous factor of a quarter. The Hawking factor of a quarter. A black hole has an entropy associated with it, which is a quarter of the area of the event horizon. When you measure area in Planck lengths. So there's an h bar down here to indicate this is a quantum phenomenon. This is essentially Planck length squared here because of Newton's constant equal to 1. Notice, classically, if you take h bar to 0, the temperature vanishes and the entropy becomes infinite. So classically, the entropy of a black hole is infinite. But in the real world, of course, h bar is non-zero, so the entropy is finite. The second law of black hole thermodynamics, or the second law of ordinary thermodynamics, says the entropy never decreases in any physical process. Is that a new question?
Go back to the zeroth law, and if I have a black hole and somehow if I can divide it into 2 black holes, or 2 black holes merging to the same black hole, then how would that service work?
Well, one black hole can never go into 2, but you could certainly take 2 and put them into 1. Each individual black hole would have a separate surface gravity and a separate temperature. You combine them together, the combined object would would have a surface gravity and a temperature, which is the combination of the other one. The thing that you add is the area. The entropy would, you'd add the areas to increase the entropy.
Do I have a corresponding picture to the classical picture that if I combine two objects with same temperature, then after that the combined objects still have the same temperature? Do I have some corresponding description?
I'll say more about that later.
Okay.
Black hole thermodynamics, at the moment, I'm going through the similarities between black hole thermodynamics and ordinary thermodynamics. But there are also differences, and I'll highlight the differences later. That's one of them. You can't take a system and break it up and combine it in the usual way that you would for ordinary thermodynamics. Okay. So the second law of ordinary thermodynamics says entropy never decreases. So if entropy is proportional to area, the statement for black holes would be that the area, the total area of a black hole, or a bunch of black holes, when you combine them together, will never decrease. And there's a qualifier here. This is true classically, because in a minute I'll be discussing when this is actually violated. The total entropy, of course, always increases. Just to put some numbers on this, if we work out the entropy for a solar mass black hole, it's huge. It works out about 10 to the 78. So you take an object with the mass of the sun, a radius of 10 kilometers, something like that. That would be equate to a black hole with the mass of the sun. And you work out the area of take the area of a sphere that's 10 kilometers in radius, and work it out in Planck units. So you use 10 to the minus 35 meters as your length. It works out as 10 to the 78. So the entropy is huge. And that has implications for the third law of black hole thermodynamics. In ordinary thermodynamics, one statement of the third law is that you can never achieve zero temperature in a finite number of steps. So for black holes, that would translate to you can never achieve zero surface gravity in a finite number of steps. And that is believed to be true in general relativity. However, there's a tension here. There's another statement of the third law of black holes. Another statement of the third law of thermodynamics, that the entropy should vanish at zero temperature. And that's not true for black holes. It's quite possible to make a black hole with zero temperature. In fact, we believe they exist. For a rotating black hole, if the black hole starts rotating, there's a maximum angular momentum. Because if it spins too fast, it begins to break up. And the maximum angular momentum is called the extremal case. And for an extremal black hole, if you go to make it rotate as fast as possible, the temperature decreases as you spin the black hole on. I haven't written the formula down. This Hawking's formula for the temperature here is 1 over 8 pi, and that's true for a Schwarzschild black hole, which is not rotating. If you make it rotate, the temperature begins to drop for the same mass. And for a maximal rotating black hole, for an extremal black hole, the temperature goes to 0. So you can have black holes whose temperature is 0, but whose mass is the order of the sun. So the entropy, the event horizon is still the same, 10 kilometers for a solar mass black hole. So the entropy is still of the order of 10 to the 78, but the temperature is 0 for an extremal black hole. So there's a tension there between the two statements of the third law. It's not a paradox, because the statement that the entropy should vanish at 0 temperature assumes that the ground state is non-degenerate. So what this is telling us is, I'm not going to say anything about quantum gravity in this talk, but whatever the underlying theory of quantum gravity is that lies behind black holes, it has to allow for highly degenerate ground states. And I think that's telling us something about the physics, because usually nature doesn't like degenerate ground states. If you have a ground state that's degenerate, perturbations will lift the degeneracy. Nature abhors a degenerate ground state. Usually perturbations will lift the degeneracy and the ground state will be unique. Not always. It can happen that if there is some symmetry protecting it, so some symmetry protecting the ground state from having its degeneracy lifted, then the degeneracy of the ground state can be non-zero. But a symmetry that gives you this kind of degeneracy must be pretty powerful. So I think this is telling us something about quantum gravity, whatever your favourite theory of quantum gravity is, be it string theory or loop quantum gravity. gravity or whatever, that there has to be, your theory has to have some very powerful symmetry that will protect the ground state, that will allow for highly degenerate ground states without the degeneracy. Okay. So, an immediate consequence of Hawking result is that black holes will radiate with thermal energy. If we focus again on the structure of black hole where the temperature is inversely proportional to the mass, if the black hole radiates energy, so thermal radiation is radiated out to infinity, then the black hole is losing energy. Total energy must be conserved. If it's losing energy, the mass will go down. If the mass goes down, the temperature will go up. So it will radiate even more. Black hole is negative heat capacity, which normally in a thermodynamic system that would be unacceptable. It would just imply that there's some instability. And the same is true here. There is an instability. Black holes are unstable against Hawking radiation. They will radiate and lose mass, and as they lose mass, they radiate even more. So they are unstable. So under Hawking radiation. So one can ask, does this make sense? How can you be talking about a thermodynamically unstable system? Well, if you work out the time scales, it will radiate with a power which of course is proportional to the Stefan-Boltzmann law. So the fourth power of temperature times the area. The temperature is inversely proportional to the mass. The area is proportional to the mass squared, excuse me. So the power will be inversely proportional to the mass squared. So let's estimate the lifetime. Just take the power, take the mass divided by the power. That would be a rough order of magnitude estimate of the lifetime. It's proportional to the mass cubed. And I've kept the h bar in here, so we see as h bar goes to 0, the lifetime becomes infinite. It's stable as h bar goes to 0. And if we put in the mass of the sun in here for a solar mass black hole, the lifetime is many, many orders of magnitude greater than the age of the universe. So even though they're unstable, the instability is such that a solar mass black hole can hang around for the age of the universe quite happily. And it makes sense to talk about it in a thermodynamic context. So, although it's unstable, it's meant stable. It's decay is so slow that you can still use thermodynamic concepts. And to get a black hole whose lifetime is the age of the universe, about 10 to the 10 years, it will need to have a mass of a tiny mass of something like 10 to 12 kilograms. And there's no known physical process to produce black holes with such a small mass. However, if the black hole is shrinking as it radiates, and this is what I want to go on to next, one should ask, I've said it's got negative heat capacity, but is this heat capacity constant volume or heat capacity constant pressure? I haven't mentioned anything about pressure or volume yet. So that brings me to the main topic of this talk, which is the role of pressure in black hole thermodynamics. The form of the first law that we learn as undergraduates is usually this, that the change in internal energy is TdS minus PdV, where V is the volume of the system and P is the pressure. And I've not mentioned pressure or volume at all. But in the context of general relativity, there's a very natural candidate for pressure, and it's what Cliff was talking about yesterday. The cosmological constant in Einstein's equations is a pressure. So if we include so far I've been talking about black holes, which with no cosmological constant included, but there are solutions of Einstein's equations where you have a black hole in the background of a cosmological constant. So if we include a cosmological constant, then we know that will induce a pressure. And for a cosmological constant, the pressure and the energy density are equal and opposite. That's characteristic. If you like, you can think of this as being an equation of state, but the cosmological constant. And a positive cosmological constant gives you a negative pressure and vice versa. Again,